So now we have a max heap. So we build a max heap. Yeah, so we have the max heap property there. Then, now we can start the heap sort. The first step, we know the element at the root node is the maximum, contains the value of the maximum, yeah, based on the max heap property. Yeah. So we can put it in place immediately. Yeah. To put it in place, we know the right position for the maximum element is at the end of the array. So we do one swap. Yeah. All right. Yeah, so in the tree, in the heap, its current location is the first element in the heap. But we need to put it in the last location of the array. So we just do one swap operation. Yeah. All right. So one swap between these two nodes, we put it in place. Yeah. After we put it in place, we can exclude it from the consideration because we never need to touch it. It's done. Yeah. So we update our heap, our current max heap. We can eliminate the last element from our further processing. Okay? Yeah. So after that, our heap size is reduced by 1. Yeah. Okay? Yeah. But the next step, because after the swap, you can see the max heap property will be violated, right? Yeah? Because of the swap, the max heap property in general, yeah, so it will not hold. So we need to fix it. We need to run max heapify operation to recover the max heap property. Yeah. All right. Yeah. To do that, because we only do one swap operation between these two elements, right? All the other elements we do not touch. That means the dirty elements, the only dirty elements appears at the root after the swap. That node is dirty. So we need to fix the violation of the max heap property starting from the root node. So we run max heapify operation from the root node. Yeah. Keep track of it until we make it clean. Yeah. So we follow the path. Okay? All right. For the worst case, yeah, because the path, there are many different possibilities. But for the worst case, when we estimate, we use the worst case. You need to follow a longest path. One of the longest paths to fix the problem. Yeah. All right. After you fix it, you get a max heap again. After you get a max heap, then you can do the same thing, because after you get another max heap, the current maximum element is at the root. You can put it in place by one swap operation, right? The second time, another swap operation. Then exclude it. Then, because of the swap, then you need to run max heapify operation to fix the problem. Yeah. Every time you reduce the heap size by 1, yeah. So keep doing things like this until you put all the elements in place. That's the heap sort. That's the heap sort. Okay? Yeah. So here you can see we need to rely on the max heap property. Yeah. Max heap property. Yeah. Yeah. All right. Yeah. Next, we need to estimate how many comparisons, how many swaps do we need? Yeah. So for the worst case, we need to look at that question. Okay. All right. Yeah. So the pseudocode, we swap A of 1 and A of n. Yeah. After that, we need to recover the heap structure. Actually, recover the max heap structure. Yeah, not just heap, right? Yeah, because we need a max heap property. Max heap structure. Yeah. All right. To do that, so we run max heapify operation. Yeah. All right. Yeah. Sorry. Oh. Yeah. What? Yeah. Why? Yeah. Iteration. Yeah. All right. Iteration. Yeah. So here, this slide we look at from beginning to end. Okay. Yeah. So how do we do the heap sort from beginning to end? Yeah. Procedure of heap sort. At the beginning, we need to build a max heap. Yeah. So we have the process to build max heap. Yeah. Remember, we use bottom up. Going through all the local triangles, right? Build a heap. Yeah. After that, we need to run a for loop, but we do iterations from n down to 2. Yeah. Because the first time when we put our first element in place, our heap size is n, right? So I equals n. This I means the current heap size. Yeah. The last iteration, that is the smallest heap size, I equals 2, because when I equals 1, we do not need to do anything, right? When I equals 1, we just drop it in place automatically without doing anything. Yeah. So that's why our iterations run from n down to 2. Yeah. For each iteration, swap A of 1 and A of I. Yeah. So I is the last element in the heap, in the max heap. Yeah. So we put it in place. All right. But after that, we need to recover the max heap property. We update the heap size. Heap size reduced by 1. So then we need to run max heapify process or function. A array comma 1. That one means the location to run the max heapify is at the position number 1. Root, right? Yeah, that's the root location. Yeah. So we do it at the root location. Yeah. All right. Yeah. So that we're using the for loop. Okay. All right. Then, very simple, we complete the heap sort. This way, this is the main idea of the heap sort. We complete it. Okay. All right. So here you can see there is one thing. Now, remember, last time I talked about a concept called in-place algorithm. Here, I want to make some comments about the in-place algorithm. Yeah. In-place algorithm. The meaning. Remember, the meaning is extra space used, right? Extra space used in big theta of 1. Big theta of 1. That's the in-place meaning. Now let's look at if our heap sort has that property. All right. You can see when we do max heapify operation, we only do swap operation, right? Swap operation, the extra space used very little. Yeah, just one or two extra locations. Another thing it can tell us max heap. Remember, here you can see we do not do recursion. We use the for loop. We do not do recursion. We use the for loop. Why? Because when we use recursion, think about, we need to use stack. We need to use a stack data structure in main memory to hold intermediate results. That stack could be very deep. It uses a lot of memory resource. So from the consideration of that may violate the in-place definition of in-place algorithm. But here, we avoid it, okay? Here, we use iteration to avoid it. But also, when you build a max heap, remember, when you build a max heap, you need to look at your code. In our pseudocode, we use recursion, okay? If we go back to our, previous lectures, you will see when we build a heap, we use recursions. Yeah. But that recursion, we can modify it to make it for loop easily. Yeah. So that recursion just for, for convenience. Yeah. It may not be necessary. Yeah. So for the heap, because that structure, we can switch to iteration easily for the heap. Yeah. So that means if you really want it in place, you need to change your code from recursion to iteration to reduce the size of the stack. Then you do not need to use stack. Yeah. So that's another important point. Yeah. Otherwise, people just ignore that recursion part. Yeah. But when you run it, you still use a lot of memory because you have recursion. Okay? So that's a potential problem. Yeah. All right. Yeah. After that, now we can do the estimate. When we want to see how much work do we need when we do a heap sort. Build a heap, we did before, right? Yeah. So we already estimate this build a max heap, this step, we need a big theta of n. Yeah. Yeah. So that's, not too much. Yeah. So we can accept it. Yeah. All right. But for this for loop, how much work? How much comparisons and swap operations do we need? Yeah, we need to estimate. All right? Yeah. First, after swap, we need to run max heapify. But the max heapify, think about it. We go from top to bottom, right? We follow a longest path from top to bottom. How many comparisons? Yeah. Log base 2 of n, right? So when the size is n, yeah, because your longest path, that's the height, log base 2 of n, right? Yeah. After that, you reduce the heap size to n minus 1. Yeah. Then the next term, you need a log base 2 of n minus 1 and so on. Right? Yeah. So you need to take summation of all these log numbers on the consecutive integers from n down to 2. Yeah. So that's the amount of work you need to do. Yeah. All right. So here I want to do a very quick estimate. Yeah. Fast and a quick estimate. Yeah. Yeah. It may not be very very tight. It may not be a very tight estimate. Yeah. Very loose. Yeah. That means each term. So for each term, here, for each term less than or equal to log of n, right? Each term less than equal to log base 2 of n, right? Total, we have n minus 1 terms. Yeah, we just take n terms. Okay? Total n minus 1. Yeah, let's just, we use n. Yeah. So n times log base 2 of n. Yeah. When we do a very rough estimate, we have big O of n log n. Yeah. So that's good enough. Yeah. All right. But some of you may think, can we use some very tight? Yeah, we can apply some math technique to do some very tight estimate. Yes, we can do it. Yeah, we can do it. Here, I can tell you the result. We use definite integral. We can do that. Okay, all right? Yeah. Log base 2 of n, 2. Yeah. So we draw the height. So this height is log base 2 of 2. Log base 2 of 3. 3. Yeah. Log of 3. Yeah. And so on. All right. Log n. Okay. Log n here. All right. Then to estimate, we draw rectangle, the area rectangle. Yeah. That the area of this rectangle corresponds to the last term, right? Then log base 2 of 3, the area corresponds to the second to last term, right? And so on, right? Yeah. Then the last area of triangle, that area, so n here, n plus 1, all right? That area corresponds to the first term. Then we add them up. Is it approximately the area under the curve? Okay, so this function is log base 2 of x, right? So that means we estimate the integral from 1 through n plus 1, and the function is log base 2 of x dx. Okay, so we use this definite integral. We can do a much better estimate, but the result is the same. Okay, the constant will be different. Result still big O of n log n, but we reduce that constant. But for big O notation, that constant is not important, right? Yeah. So for that reason, yeah. So we have this big O of n log n. Worst case. Yeah. So worst case. Yeah. Yeah. For other cases, yeah, actually, for other cases, also, yeah, for the you may talk about best case, right? Yeah. Yeah. So the best case, because we have a near complete binary tree, yeah. So the best case slightly better, yeah, but still n log n, still n log n, because near complete binary tree. Yeah. All right. Yeah. So that's the part A. Now I need to jump to part B to one slide to make some comments. Yeah. Yeah. Part B, yeah, so we finished the multiplication method. Yeah, just one slide to talk about a perfect hash function. Yeah, yeah. Just let you know, I just posted quiz number 5 in Canvas under title of Module 5. Quiz 5 covers Module 4, Part D, and Module 5, Part A and Part B. 3 parts. All right. Some of the questions related to the slides I'm explaining. All right. A perfect hash function. We know the performance of a hashing algorithm closely related to your hash function. How good is a hash function? So let us look at, so what is a perfect hash function? The perfect hash function has this property, always map 2 keys to 2 different slots. That's the perfect. That means no conflict, no collision, right? No collision problem. So when you map 2 keys to the same slot, there is a collision problem. Then you need to resolve the collision by more hashing steps. More hashing steps. Here I didn't talk about other hashing techniques to resolve the collision problem. All right. So the answer is there is no perfect hash function. No matter how do you design your hash function, you can never get a perfect hash function. Okay? Sooner or later, you will encounter the situation that 2 keys could be mapped into the same slot. So the collision problem cannot be eliminated. So you will have some collision problem. But we want to control the percentage of the collisions. Percentage. So we want to make the percent of the collision very low. Then it's a good hash function. Percent, the rate of the collision is very low, then you have a good hash function. All right. So the collision problem, 2 keys are hashed to the same slot. That's the collision problem. And there are some techniques. After you get a collision, you need to select a few more hash functions. So that is after our primary hash function. We have a first hash function, primary hash function. But after you get a collision, you need to run a secondary hash function. So then, probably a few more times, to, because you need to find a location for the second key. You need to allocate a different slot to the second key. Because the current slot has been occupied by another element already. So then you need to find a different slot for the new element. All right, so that's the, this perfect hash function. Okay. All right, so we finish part B. Now I can move to the review session number 1 for the final. Wednesday, review session number 2. All right. First, let me talk about the final. Some students asked at the beginning of the class, So let me give you more information about our arrangement for the final exam. All right, yeah. So based on our syllabus, yeah. So it's there, yeah. But now I just, explain a little more final exam of this class. All right. May the 11th, Monday next week. Yeah. Today, May the 4th. So plus 7, May the 11th. Okay, all right. May the 11th. Monday. Time, same as our class time, right? 5:30, our class time, 5. Yeah, so here it's for the in-person class, but I also have an online class. Online class, almost the same. The only difference is everything is online. Yeah, the time, yeah. All right, so I will go there. So for you, 5:30, because 2-hour period, 7:30 p.m. No. All right. Then, the questions. No questions. The total, you just look at our typical homework assignment. And also the midterm. That similar arrangement, but we need to do pretty much the same amount of work in the final, right? Yeah. So here, for you, in-person students, but for online students, I just modify slightly. Yeah, change it to online version. Yeah. All right. So for you, Part A, Part B, Part C. Yeah, this time we need to use A, B, C. Midterm, we do not have C, because midterm you have online, right? Completely online. So that do not need to split Part B, Part C. But now you have the in-person. So I need to split Part B, Part C. Yeah. So let me give you the details. All right. Part A, so it's online, right? Now, Part A, the same as quiz number 6, our last quiz, Canvas quiz. So you know the meaning, our typical quiz. All right, so that's online. Okay, all right. And you also know it's 10 concept questions, right? Yeah. Concept questions. Covering module 4 and 5. Okay? Yeah. Only modules 4 and 5. 2 modules. Okay? All right. And start after your in-person test, right after. Okay, so I make it 7:30 p.m. Same May 11th. Okay, all right, Monday. Start. And same as Part C. Yeah. So, all right. Here. So when I talk to Part C, I'll give you the time and the time together. Part B. Part B. 10 basic computation questions. 10 basic computation questions. Okay, all right. And also from module 4 and 5. Yeah. All right, module 4 and 5. Yeah. All right. And yeah. So the time, because this is in person, yeah. So the test time, 2 hours. Okay. Yeah. 2-hour test time. Yeah. For online students, yeah. ABC, the same period of time. Okay. ABC I post all together, so same period of time. Yeah. For in-person, part B. Yeah. So you need to do it in the 2-hour period. Yeah. Then part C. Five challenging questions. Five challenging questions. Okay, all right. Yeah. The start time, yeah, actually the start time, 7:30 p.m. Same, so after part B. Okay. Then, end time, so part A and part C, same end time. And, oh, sorry. Actually, I want to use this blank slide here, but anyway. Yeah. All right. And Friday. Yeah. So this is Monday, right? Yeah. Monday. Yeah. So 11th, Monday. 15th, Friday, right? Yeah. So I'll give you a Friday. May 15th, Friday. This many days. Okay? Yeah. I'll set a deadline. Yeah. Yeah. So for part A, part C, yeah, I set the same deadline. Online. Yeah. Yeah. So part C also online. Yeah. So I just put online. Okay. Okay. Yeah. Yeah. So that's the arrangement for the final, for your in-person class. Yeah. Yeah. So for online students, part B, because when you, part B, I will make the assignment available at the, yeah. So for online, I can make the 3 assignments available at this time. Okay. Yeah. Yeah. This time. Okay. Yeah. So I make those 3 assignments same time. Starting time, same starting time, and the same end time. This end time, start time. Yeah. All right. Yeah. Try. So that's the our plan. Okay. Yeah. The policy. Yeah. Policy. You can bring your laptop. You can, access our notes, books, online. Yeah, so online tools, you can use online calculator. If you need to do calculation, you can use online calculator, but you cannot use online search engine, AI tools. You cannot use online tools to find the answers. Okay? Yeah. So only calculator and our class materials. Okay? When you use your laptop, you can only use calculators and our course materials. Okay? Yeah.
That would be for part B, right?
Yeah, for part B. Yeah. Oh, yeah, good. Yeah, for part B. For part A and C, then just like your homework assignments. Yeah, good. Yeah, good question. Yeah, only for part B.
And that would cover module 4 and 5.
Yeah, module 4 and 5. Module 5, because you do not have a chance to practice module 5, so here I need to give you a few examples, module 5. Yeah, so you just based on these examples to do some module 5 questions. Yeah. All right, so I have 22 minutes. I will give you a few examples on module 5. All right. I try to complete. The first question, yeah, here I'll give you four examples, module 5. The first question, given a max heap whose values correspond to the array indices from 1 through n. Yeah. So that's our typical arrangement. What is, here the question, what is the smallest possible index for a node with height 2 in the heap? Okay? Now, height 2, the meaning, height 0 leaves, right? Leaves height 0. Then another level height 1. Yeah, height 1. Here, height 2. Yeah, all right. Let me show you how to find the answer. We need to draw a diagram. So here, let me draw a line segment representing the, array corresponding to this max heap. Yeah. Position from 1 through position n. When we start, first, let's look at the portion corresponding to the leaves. Yeah. That means height 0, right? So height equals 0, so the leaves part. Yeah. The range, look at the range of the leaves, right? Yeah. The range is, based on our formula, n over 2, floor function, plus 1. Okay, that's the range. Okay, range for the leaves. All right, height 0. Then, next interval, we need to look at the next interval corresponding to height 1 nodes. Yeah. So let's use this. Height 1 nodes. Okay. Yeah. H equals to 1 internal nodes. Height 1. Yeah. All right. Let's look at the range. Range, yep. Yeah. Because this is n over 2, right? Yeah. The one right before this, left end of the range of the leaf interval. Yeah. All right. The lower part, n over 4 plus 1. Yeah. This is the range, okay? Based on our formula. That is the range. N over 4 plus 1. Okay? Yeah. All right. But now we need to look at height 2, right? Yeah. Height 2 interval for height 2, h equals 2, and for the range, this point should be n over 4 floor function. Okay? All right. Then this lower bound, n over 8, right? Yeah. Plus 1. This is the range. That is the range. Okay? All right. Yeah. Now the answer. Yeah, because smallest possible index, is it this? Yeah, because this is the index number, right? This is the index number. So the answer is this expression. The leftmost index number in the range for height 2. For height 2. Okay? Yeah, that's the answer. Yeah. All right? Yeah. Yeah. All right? Yeah. Okay? So you can see, yeah. We need to use the ranges for different levels of nodes. 0 level, height 1 level, height 2 level. Yeah. All right. That's the first question. Second one, given a heap with n nodes, if we know there are 40 leaves in the heap, what are the possible values you can take for n? Yeah. The number of leaves is known, 40. Okay? 40. The question, what is the formula for the leaves? Okay? Number, so we need a formula for the number of leaves with n nodes. Yeah. So remember we have two expressions. One, n minus floor function n over 2. Another, just the one term, the seeding function of n over 2. Right? Yeah. Okay? All right. So here, to get all the possible n, so here we need to find, because you may get more than one such n, right? So you need to find all the possible n such that the number of leaves equals 40. Yeah. But here we have floor function, seeding function. Yeah. So when we work on floor function, seeding function, it is not quite straightforward, right? Yeah. Because there are cases. When we work on floor function, seeding function, there are several cases we need to consider. Okay? Yeah. So here we need to see how to handle those different cases. Yeah. So here, first we do approximation. First step, we do approximation. Okay? Yeah. So let's take this one term. Okay? Yeah. So n over 2 seeding function. This one term thing. Yeah. Yeah. So then let's take out that seeding function. Let's just use n over 2 equals 40 and see what happened. Yeah, because for approximation, okay? Yeah. Approximation, we just want to get approximately what is the n value approximately, okay? So this give us n equals 80, right? Yeah. Yeah. So our approximation step, we get a approximate location for n, okay? Approximate location for n, all right? So we use this approximate location as our starting point for other possible values. All right, yeah, so here, let's draw a line. Yeah. So we need to look at the n values. Yeah. 80 is 1, and other 81 nearby values we also need to look at it, right? 79, okay? Yeah? All right. So look at it, when n equals 80, you plug in the formula, seeding function of 40 is 40. So 80 works, right? It's satisfied condition. So 80 is the answer, one of the answers. All right, all right. Then you try 81. If 81, 40.5, seeding function 41. So it's not the answer. Okay? Yeah. If it's not answer, that means we do not need to look at it further. Yeah. So that means stop, right? Yeah. If 81 not the answer, that means all other values higher than 81. We do not need to look at it. Okay? We can stop. Let's look at 79. 79 over 2, yeah, 39.5, right? But you take seeding function. Take seeding function. That means also 40. So 79 is our second possible n, right? Yeah. So, yeah. Then we need to look at 78. 78, 39, 39 seeding function, no, 39, right? So, yeah, yeah. So at the right-hand side, when you get the wrong number, you can stop. When you go left-hand side, when you get the wrong number, you can stop. Okay? So these two numbers are the possible answers, 79 and 80. Now, the idea is like this. Okay? All right. Yeah. The next question, we have a similar question. Yeah. Similar, we need to do, yeah, but a little harder than this one. Yeah. All right. Question number 3. Given a heap with n nodes, if we know that there are 60 nodes with height 1. Yeah, this time. A little harder because the number of nodes with the height 1. Okay, all right. Height 1. Yeah. In this heap, what are the possible values you can take for n? Yeah, this time. Height 1. Okay? Yeah. All right. Yeah. The first thing, yeah, we use the similar idea, but formula is slightly different. We need to use the number of height 1 nodes, right? Yeah. Number of height 1 nodes formula. We need to get a formula for number of height 1 nodes. Okay? Yeah. Yeah. So let me recall the range. Yeah. The formula. So you can find it from your notes. Yeah. The range. Height 1 this time. H equals 1. Yeah. The upper bound, yeah, n over 2, right? Floor function. The lower bound, n over 4, floor function plus 1. Yeah. So that's the range. Yeah. So we need to count the number of elements in this range. And inclusive, we need to include both endpoints, inclusive. Okay? Yeah. So that number, yeah, so we did that before. The upper bound n over 2 floor function minus the number right before the lower bound. Yeah. We cannot minus lower bound, but the one right before that lower bound. So n over 4 floor function. That is the formula. And in this formula, we know equals 60. Equals 60. Then we need to find all the possible n values. Yeah? So let's use the same method we used in the example number 2. Okay, all right. First, approximation. We need to find approximate location for n. Okay, yeah. We just take away the floor function, okay? Yeah. N over 2 minus n over 4, yeah. That is n over 4, right? Equals 60. Yeah. So we have n equals 240, right? Yeah. 240. All right. So that. So this is the n, 240. Then we look from the extended to the right right extension and the left extension, 241, 242, okay? Yeah. Left-hand side, 239, 238. So then we plug in and check, okay? When we plug in 240, we can easily see it works, right? Yeah. All right. 241 over 2 floor function minus 241 over 4 floor function. The first one, 120, right? The second one, 60. Yeah, it works, right? Yeah. 241 also works. Okay. 242. 242 over 2 minus 242 over 4 floor function. 242, that's 121, right? Minus still 60 doesn't work, right? So it doesn't work. So we can stop, okay? Yeah. When we extend to the right, we can stop at 242. To the left, yeah, to the left. Yeah. 239 over 2 minus 239 over 4. Okay? Yeah. Minus 119, right? Minus 530, 59, right? 59. All right? Yeah, it works. Yeah, 60. Yeah. All right? It works. Yeah. 238. Yeah, 238 over 2 minus 238 over 4. Okay? Yeah. Also, 119, right? Minus. Also 59, right? Equals 60. Yeah, so also works. 239 works. All right. 237. Yeah. 237. Okay. All right. 237 over 2 minus 237 over 4. Yeah. Then 118, right? Minus still 59. Yeah. Equals 59. Yeah. It doesn't work. So we can stop. Okay? Yeah. So we find 4 possible numbers for n. Yeah. Yeah. So 4 answers. All right? So that's the, general method you can use. Yeah. Otherwise, it's not easy to handle the floor function, ceiling function. Right? It's not easy to handle floor function, ceiling function. Yeah. All right. The last example. Given a heap with n nodes, if we know there are 100 longest paths from root, what is the smallest number for n? Yeah. This one, a little harder. Yeah, let me do the analysis. Yeah. So we have a heap. We know it is a near complete binary tree. Near. All right. So what's the meaning of that? Near complete. That means up to. Yeah. So if we do not look at the bottom level, it's a complete. Yeah. So, yeah. Above the bottom level, it's a complete. But bottom level, we have, some more nodes. Yeah. But it could be incomplete. Yeah. Yeah. So there are some, some part we may not have nodes. Yeah. That's the typical structure of a heap. Okay. All right. Now we need to find the smallest number such that there are 100 longest path from node. You can see the longest path from the root to the bottom corresponds to this bottom level, right? The number of nodes. So these nodes corresponds to longest path. Okay? So that means this part, the number of nodes, that part is 100. 100 nodes in that part. All right? Then, all right. And let's estimate the number of nodes. Estimate. And minus the number of nodes above the bottom level, right? So let's use 2 to the k minus 1. Yeah, because it's a complete number. So this number, it should be 100. Okay? That should be 100. All right. Yeah. So we can write n should be equal to 99 plus 2 to the k. So now we only need to figure out that k, that little k. Then we can get the answer for n. All right. To get that k, we need another condition. Yeah? Yeah. Yeah. Because the bottom level may not be full, right? It could be full, but it may not be full. So that means n should be also less than or equal to 2 to the k plus 1 minus 1. Yeah. Yeah. Because when the bottom level is full, the equal sign with n equals this 2 to the k plus 1 minus 1. Okay? Yeah. All right. So our k, our n should be in this range, 99 plus 2 to the k. Yeah. And we want to find the smallest such n. Smallest such n. All right. All right? Yeah. So we do it from the lowest possible level. All right? Yeah. So, yeah, I can. Yeah. So we can complete quickly. All right. Yeah. Because 99, n greater than 99 plus greater than 100, that means this number is greater than 2 to the 6th, right? 2 to the 6th. 2 to the 6th is 64, right? 64. So n is greater than 64. That means k should be greater than 6, right? K should be greater than 6. Okay? If k is greater than 6, let us try the smallest possible number for k. K equals 7. Okay? Yeah, because we need to pick k greater than 6. The smallest k greater than 6, it's 7, right? So let's try k equals 7. So n equals 99 plus 2 to the 7th. 2 to the 7th is 128, right? 128. Okay? All right. Yeah. So 207, 27, right? 227, yeah? So n equals 277, and let's check the upper bound. Upper bound, 2 to the 8th minus 1 equals 255, right? Yeah? Yeah. So n less than 255. So this inequality is satisfied. So the answer is 227. Okay. Because when we try k equals 7, the condition is satisfied. Yeah? And the smallest possible k corresponds to smallest possible n. Yeah. So this is the smallest, 227 is the smallest possible n. Yeah, that's the answer. Yeah. All right, yeah, that's it. Yeah. So on Wednesday, I talk about your homework.